Welcome to our video presentation of the written report of the case study, bungee jumping. Our document is divided into phases. In phase 1, we analyze the movement from the moment of the launch of the athlete until the bungee rope reaches its natural length. And in phase 2, we continue until the athlete reaches the lowest point. For phase 1, we're going to analyze the forces and initial conditions, taking into consideration mass, which is the mass of the athlete, gravity, as the acceleration due to gravity, constant on Earth's surface, the initial position, x of 0, which is in this case 0, since we are starting from rest, the initial velocity, which is the derivative of the position, also 0, the acceleration, which is the second derivative, but in this case is due only to gravity, so it's equal to g, the constant b for air resistance, and the rope length, L, which is the length of the rope, natural, and stretch and contract. For the differential equation, we have that without air resistance, m times x double prime equals mass times gravity. But with air resistance, we add the constant b times the velocity. We notice that we have that in a subtraction because it's going in the opposite direction, since we're taking that the mass times gravity is the positive direction. So for without air resistance, first we can cancel the masses out and we get that x double prime equals gravity. So in order to find the velocity, we take the antiderivative and we integrate this equation with respect to time, and we are left that x prime equals g times t plus c. We use our given initial values, which is that when time equals 0, then our velocity equals 0 as well, since we're starting from rest, and we can find the value of c with that. So we substitute and we get that c equals b sub 0, and our final equation is that the velocity with respect to time equals gravity times t plus the initial velocity. Once we have the velocity, we can integrate this equation again in order to obtain the displacement or the position. So we take the integration with respect to time, and we get that the displacement is equal to 1/2 gt squared plus b sub 0 times t plus c. And we do the same in order to find c. We use our initial values, which is in this case that when times equals 0, then the position is equal to the initial position. So we substitute and we get that the c is equal to the initial position. And we are left that the position of the athlete at time t is equal to 1/2 gt squared plus b0 times t plus the initial position.
To find the general equation for the air resistant, we started from the equation mx double prime equal mg minus bx prime. So first, we have to simplify and distribute the equation and rewrite it as a second order derivative. That is the one that we have shown there. After that, we have to get the general solution. And to do that, we firstly need to find the homogeneous equation by setting this equation equals 0. After that, the characteristic equation had the form of r squared plus b divided by m r equals 0. So we factorized r and find that the roots for r is equal to 0 and minus b divided by m. For that, then we have to do the complementary equation, which is that one showed there. Then we get into C1 plus C2 Euler minus B divided by M. So after that, we have that the particular equation and its derivatives are the ones that is shown there, yp prime, and yp double prime. And we have to substitute it in the homogeneous equation to find the coefficient of A, which is the one that we show there in yp. After that, we get the general solution that is the y complementary plus the y prime, and we get that y of t is equal to c1 plus c2 Euler minus b divided by nt plus gm divided by bt. Then we had to find the constants c1 and c2, assuming that for the initial t that is equal 0, we had an initial position of 0 and an initial velocity also of 0. Then evaluating for y0, we get that c1 is equal to minus c2, and we found c2 in the velocity, initial velocity, getting that c2 is equal to gm squared divided by b squared, also getting c1, which is the same but with opposite sign. After that, we plug these values in the final equation, and we get that y of t is equal to minus gm squared divided by b squared plus gm squared divided by b squared, Euler minus gm divided by bt. And final, we plotted it, and we get the free fall of the subject in the bungee jump.
Now we're going to analyze the phase 2, that is the analysis of the trajectory when the rope is more than its natural length, so it stretches. For this part, we have the same initial conditions, but the xi and x prime I are the final conditions of the phase 1. We also have to include Hooke's law, that is the coefficient of elasticity of the rope, into account. Then we have that our differential equation is mx double prime mg minus bx prime minus kx. We're not going to do without air resistance this time, just with air resistance, so our answer is more complete. First, for the solution, we have to redistribute it so it can be seen as a non-homogeneous part and a homogeneous part. So first, to solve this, we have to take the complementary solution of the homogeneous part, but there is something that, because we're only working with constants, there is actually 3 cases that can happen after finding the roots. And the first case is when we have 2 real solutions that we use this for. In this case, it's not optimal because a high acceleration is reached, the acceleration doesn't decrease. And in a real scenario, this will be like very dangerous because the rope could break or we could go to the ground, a lot of things. The second case is basically the same, but only with one real solution. This is a form. And the third case is actually the optimal case where we have both imaginary solutions or complex. And in this case, because we have cosine and sine, the acceleration actually starts to oscillate and starts to decrease the velocity, and it will reach a terminal point at the end. But we will see that later. And for the particular solution, it's quite easy. We have the form A because it's a constant, and then we take the derivatives that both are 0. We substitute to take the value of the coefficient A. Then just we substitute it and have the particular equation. We add it to our complementary equation, and we have our general solution. And with this general solution, we can't actually have the values of C1, C2 because of the constants, but we made an approximation with some typical values of all these constants. And this was the graphic that shows to us that we can easily see how it has a position at first, how the position changes very fast, and then it starts oscillating with each time less amplitude. So it gets to an equilibrium point, terminal point when it stops. And well, yeah, that was all, and thanks.